which gives us a level in a tank, 0 to 100%, or maybe in millimeters of water or whatever. And we have a level switch. Level switches are used when we get to certain values. You have high level switches, low level switches, that sort of thing. So first we're going to look at analog type level sensors. In the modern world nowadays, the ultrasonic level sensor is the first one that we would choose. It's basically a modified echo sounder. You send out an echo pulse, it bounces off the surface of whatever it is we're trying to measure, and it comes back. By measuring the time it took to leave and come back, we know the level. Ultrasonic level sensors are pretty reliable, they're pretty rugged, and they are as cheap as chips. So they're sort of comparable prices nowadays to even a ball valve type pressure type level sensor. They're really, really cheap. And so they would always be our first choice. The other nice thing about the ultrasonic level sensor is it's not in contact with whatever it is we're trying to measure. And that's always an advantage, because maybe the thing we're trying to measure might be some sort of unpleasant chemical or something. And this is not in contact. It's at the top of the tank. So what we do is we send out pulses. The pulse bounces off the level. We measure the time it takes for the pulse to come back. It's as simple as that. And by knowing the speed of sound, we know how far away it is. Oh, going back. So this is what is called an envelope. It's basically, it looks just like a fish finder. And what it is this point here is the sensor. The sensor sends out a pulse, and each one of these little peaks down here is an echo that it gets back. This peak here is a big fat echo, so that is probably the level in the tank. You've got to imagine the whole of this thing is tipped on its side. So that's probably the tank level. Now, because we've previously set up the ultrasonic level sensor so that it knows how high the tank is, it knows how high it is in the tank, the ultrasonic level sensor can work out how high the level in the tank is. It's really simple, and it's really very accurate. We do have problems with it in that we need to know the speed of sound in the thing that we're measuring. If we have a tank that's full of ammonia, then above that tank will be ammonia gas, in which case the speed of sound is different than the speed of sound in normal air. Similarly, for oxygen, the speed of sound changes. Nitrogen, helium, the speed of sound changes. In fact, the speed of sound also changes with temperature. That can be a big problem in WA, because one of the things that's very unique to WA is the fact that we have a huge temperature shift. Day to night, in certain parts of WA, the temperature can go from 0 degrees C to 40 degrees C. And as you can see, the speed of sound alters from 332 to 355. To compensate for this, what these level sensors have, if this is my tank, and there's my liquid level, I'm going to put my level sensor at the top here, and that's beaming out ultrasonic waves, which are then reflected back. What my level sensor has is a temperature sensor built in. And the idea of the temperature sensor is it compensates for the temperature change. Now, the problem we have with WA is that we have this huge temperature shift. And the problem we have with WA is that although the temperature at the top here might be, say, 30 degrees C, the temperature at the bottom here might be something completely different. It might be 40 degrees C. So the temperature compensation is incorrect. So we do sometimes have problems with ultrasonic sensors that they'll give a wrong reading because of a temperature shift. Other problems we have with ultrasonic is that ultrasonic doesn't like anything which will absorb the sound. Things that will absorb the sound are things like bubbles. If you have foam at the top of your liquid, the foam absorbs the sound, and then it's not going to read because there's no echo coming back, and so the ultrasonic sensor just will not work. Other things which absorb the sound, which will give us problems, are dust. If this is a very dusty environment, the dust will absorb the sound, and the ultrasonic sensor will not work. Other considerations you have to take into account is if we're measuring the level in a silo that contains solids, the solid does not necessarily make a flat base like that. The solid quite often piles up like this. If we stick our ultrasonic sensor at the top here, then what happens is the sound waves come down like this, but they reflect back like this. And the sensor doesn't see them. So there are several things that can contribute to the ultrasonic sensor not being able to work. And that's a bit of a shame because they are very cheap and they're very reliable and they're, reasonably accurate. The next choice then, if ultrasonic isn't going to work for us, is radar. Now radar it's radar. It sends out, it's just like ultrasonic, but this time we're going to send out microwaves. It's sending out microwaves. Now, as soon as people start talking about sending out radiation, people get nervous. To give you an idea of the sort of levels we're talking about, we're talking about a microwave oven. Inside it, the level of radiation is about 1 watt per square centimetre. If the door leaks, we're talking about 0.005 watt per centimetre, and most microwave ovens leak at the door. Your mobile phone transmits about 2 watts of microwave energy. So that's about 0.001 watt per centimetre squared. These radar sensors, the new modern radar sensors, I hasten to add, the old radar sensors were just a bloody hazard, but the new modern radar sensors are transmitting tiny amounts of microwave energy compared to your mobile phone. And you carry your mobile phone around in your pocket. So they are reasonably safe. That doesn't mean that you switch one on and you stick it down your throat. Depending on the horn design, the radar beam will spread differently. You can have horns that spread the radar beam 8 degrees or 23 degrees. Funny thing about radar is, or funny thing about microwave is, that microwave will follow a piece of metal. Microwave will be guided. So if you transmit your microwave out into a pipe, you can make it go round corners. And that allows you to do things like measure the level inside something like a blast furnace. Well, you wouldn't want to put your electronics at the top of the blast furnace because all that heat rising would cook it. But you can put the electronics off to one side and the radar will read because the microwaves will go round the corner. That takes us to guided radar. This is what we're talking about, where we guide the radar path. Guided radar is just a marvellous way of measuring level. What we do with guided radar, I haven't got a picture to show you. What we do with guided radar is we have the radar transmitter at the top, but instead of having a cone, we have some kind of piece of metal coming out of it. Now that can either be a piece of wire or just a piece of rod. It doesn't have to be anything special, just something metal. And then what will happen is the radar pulses, or maybe I should have done that in a different colour. The radar pulses travel down the rod in little donuts. They don't escape anywhere, they just travel down in donuts. Now this is really good, because they all stay in one place. And then when they get to the level, they reflect back again. In fact, they also reflect back from the end of the bit of metal. So that if we've got a level, let me get my level. If we've got a level there, oh, I wish I'd done that in blue. If we have a level there, then the radar image we get back will be like this. It'll be high, low. It'll be no reflection, and it'll go low, and then we'll get a big fat reflection, and then we always get another reflection from the end of the bit of metal. There's two ways that we can determine the level of this tank. The first method is by knowing how long it took to get back from there. That's the first method. The second method is due to the fact that because the liquid, or whatever it is we're measuring, is denser than air, then this distance here between the level and the end of the line, in fact not that distance, this distance here between the sensor and the end of line reflection varies, it changes, because of the fact that the liquid is denser than air, and radio waves travel slower in the liquid than they do in air. So there are two methods of finding the level in the tank, and most modern sensors use both methods. The nice thing about guided radar is completely impervious to air bubbles in the liquid. It's completely impervious to dust. It doesn't give a rat's about anything, really. So guided radar is a really good method, and it's the modern method that we use a lot. If we have something which is bubbly, see, also, if this liquid down here is full of bubbles, ultrasonic's not going to like it, because ultrasonic doesn't like bubbles. Guided radar is fine. The only other things. Yeah, guided radar will be fine for detecting levels of dry powders and also levels of liquid. See, one of the problems you can get with normal radar is that if you have a normal radar up here with a cone, temperature change. The change of what we're talking about here is radar. So it's traveling at the speed of light. The difference in the speed of light with temperature change is pretty insignificant. It's not like sound, where it's totally dependent on things. The speed of light doesn't really change that much. It is temperature compensated, but it's not a big deal. Now, another problem you can get with straight radar is that if you're measuring solids, if your solids happen to be made of crystals, then what can happen is those crystals can look very, very like the shape, if you've ever seen the American stealth planes, I think they're called the F-111, I'm not 100%, but the American stealth planes that have all got the flat angles, all at different angles, certain types of crystals can look like stealth to radar, and radar just doesn't see them. Whereas guided radar will not be affected by that problem. So guided radar is definitely our next choice, especially in difficult applications. Now, one type of difficult application that we do see a lot of is if we have, I'll just draw this up quickly, a thing called a distillation tower. And what we do in a distillation tower is we put petrol in it and we heat it. We've got hot petrol in there, or hot crude oil in there. And what happens is that the crude oil bubbles through to the different levels. And the higher the the thinner the oil, the higher it will bubble. What's the name of that thing that's the strength of petrol? I've completely forgotten. Does anybody remember? No, you don't remember? Ah. When you go to the garage, you go to the petrol station, you buy petrol. No, not viscosity. Viscosity, yeah, that is the thickness of it, but not the, aircraft fuel has got a higher, and it's that word, which I can't remember. Yeah, that's got a high one as well, and I can't remember what it is. Ethanol. Octane. Thank you very much. Sorry about that. A momentary blank. The higher the octane of the fuel, the higher up the distillation tower it goes. Now, the problem we have is we need to measure the level in these different bits of the distillation tower. But it's very hard to do because everything's bubbling and boiling around. So what we do in this case is we use a thing called a stilling well. And a stilling well is a piece of pipe sitting off to one side. And the stilling well is connected to our main tank. And because there's no bubbling or nastiness going on in the stilling well, we've got a nice little level in there. So by measuring the level in the stilling well, we know what the level is in that area of the distillation tower. The old traditional method of measuring the level in the stilling well was to use a horrible thing, which was called a displacer. And a displacer was a float which was attached to a piece of chain and a bunch of levers and pulleys, and the fitters were constantly going up there and oiling it and kicking it and chewing on it and stuff to keep it working. That's the old way of doing it. Nobody does that anymore. Oh, except in WA, of course. I keep saying that because I'm afraid there's some industries in WA that are a little bit behind. The new way of doing it is you take the old displacer out, you throw it in the skip, and you put a guided radar in there. And the guided radar, they're actually built and designed to fit exactly on top of the stilling wells. And you put a little guided radar on there, and that's the last time anybody ever had to go back to it, because it just gives you a lovely little level without a problem. So guided radar in a stilling well. Stilling well's a great way of dealing with really, really unstable surfaces.